The finite element method is a numerical technique for determining various physical parameters related to some mathematical problems, and it has a huge amount of computer application, because this finite element method is highly computer compatible, because it is basically a matrix method, and mathematicians often refer this particular finite element method as one of the method solving the differential equations. Now, if you look at this particular finite element method, this involves first of all modeling the problem. That is, basically we define the physics of the problem, we give the boundary conditions corresponding to the behavior of that particular model or the problem, and then we obtain the solution. And then here, if you look at the solutions for any particular physical problem, we have two types of solutions. First one is an exact solution, second one is an approximate solution. Often exact solutions are not possible in the case of complex problems, and so generally we prefer numerical methods which give approximate solutions, and the amount of approximate and the accuracy of this particular approximate solution can be increased by varying different parameters. And so far as this particular engineering analysis is concerned, and the methods of solution in the engineering analysis are concerned, here you have classical method and numerical method. Classical methods often provide exact solutions, and of course to some extent approximate solutions. But in general, a numerical method will provide approximate solutions, and in this particular numerical methods, we generally go ahead with energy method, boundary element method, finite difference method, and finite element method. Method of solutions. In the classical methods, they offer high degree of insight, but the problems are difficult or impossible to solve. In numerical methods, it is minimization of a particular expression for potential energy of a structure over the whole domain. And of course, we have boundary element method, finite difference method, and finite element method. And in this particular finite element method, which we are very specific about, this approximates the behavior of an irregular continuous structure under general loading and constraints with an assembly of discrete elements. Okay, now if we define this particular finite element method, the definition is: finite element method is a numerical method for solving a system of governing equations over a domain of continuous physical system, which is described into simple geometric shapes called the finite elements. So this particular process of dividing a particular continuum into a number of small elements is referred to as discretization. So now we look at this particular discretization. In this particular discretization, modeling a body by dividing it into equivalent system of finite elements interconnected at a finite number of points on each element, and these particular points of interconnection are referred to as nodes. So here you have these particular nodes, and this is the system that is discretized, and here you have this particular junction points, often referred to as nodes. Okay, and if you look at this historical background, in this particular finite element introduction has started by Clough in 1960s, and of course the three-dimensional behavior is incorporated in 1970s for large deflection and thermal analysis. Also in 1976, large deformation nonlinear dynamics have started, and of course presently this particular system of finite element method is the key for the solving of the problems in most of the engineering analysis softwares. So this is the hierarchy of the development of this particular finite element methods. But the major thing has the major developments in this particular context of finite element method started in 1960 with Clough. And of course later on, earlier to that, there are a number of works done by eminent scientists as given in this particular slide. And if you look at the analytical process of finite element methods, and if you take a structural stress analysis problem, first one is conditions of the conditions that must be satisfied by the problem is that equilibrium, that is the problem should be in equilibrium, the system is to be in equilibrium while solving the problem, and then compatibility, and then constitutive law which governs the behavior of the various parameters in that particular system, and the boundary conditions, of course. And if you look at the approach, we take up force method, that is when the internal forces are known, and we take up displacement of the stiffness methods. Basically, this stiffness method is quite often used, and because it involves the formation of the stiffness matrix here in the system, and then doing it, and then calculating the problem, and solving the problem. Now, the analysis procedure for a linear structural analysis. Now, this is we have three specific elements here, or models. This is the one-dimensional model, which is almost like a line, and here two-dimensional model. Here you have, this can be defined by means of two coordinates, and of course this is a three-dimensional problem given by three dimensions. Okay, and here are number of elements. You see, one-dimensional element is often referred by this one, a small line, and the examples are a bar element in general, and 2D elements which extends in two dimensions, and here every node, that is every corner point, will have 2 degrees of freedom, both in x and y directions, to be more specific. So here these two are the 2D elements that you commonly find. The first one is a a quadrilateral element, and the second one is a triangular element. And of course, the 3D element is a brick element, in which you have 3 degrees of freedom for each node. Okay, so and of course this is the mesh that we generally do, and so in selecting or in solving the problem, first of all we have to select the element, and then we have to select the shape function. The shape function will give the variation of a particular physical parameter throughout that particular continuum. And the third one is the compatibility law, or the constituency law, which is mainly Hooke's law in the case of the simple structural analysis problems. From that formation of element stiffness matrix, in the formation of element stiffness matrix, we generally make use of either potential energy approach, direct equilibrium method, work energy method, whatever the case may be. And finally, the formulation will be something like this: K D is equal to F, where F is the force vector, and D is the displacement vector, and K is the stiffness matrix. Okay, and the equations formed, or the matrices formed through the above methods, will be generally solved by elimination method. That's either Gauss-Seidel method or Gauss elimination method, whatever the case may be. And of course, the results are interpreted. Okay. And then if you look at the application of the finite element method, this can be applied to a number of problems, almost all physical problems, both linear as well as non-linear. And of course, there are a number of softwares which are available in market, which will be making use of this particular finite element method as their backend to solve a number of analysis problems: ANSYS, Nastran, Abacus, Mark, LS, Diana, etc., etc., depending upon their applications. So that's all. Thank you.